This is the platform of Mathematica, which is a high-level symbolic mathematical language. It's very effective with visualization, the data manipulation, statistic, deep learning as well, and can solve very complex mathematical algorithms at the same time, which are very complex, compressed, and very high-level manner. So, without going into the details, I only should like to show that the general syntax of it, that there is some command, and after that, a square bracket. And within the square bracket, you can find an expression on which you have to do the command and the variables, which are the variables of this expression. And the last part is the options. There are a lot of modificating options on it. For example, consider the solve command. This can solve an equation, an algebraic equation. And if you use the dsolve, it is the differential equation and the analytical solution of a differential equation. And if you consider the ndsolve, you can see that the capital letters in the beginning of the command means that this is a series of algorithmic things, that the n is numerical, d is the derivative, and solve is to solve something. So nd is so the numerically solve a differential equation, and you have a lot of commands for the visualization as well. So as a very simple example, if you consider this equation that x squared plus 2 bracket times x squared minus 2 equals to 0, so double equal mark means that you have to solve these equations for variable x, and you consider only the real solution of that. And if you run this command, if you run this subroutine, you will get the 2 solutions of this system. So it's a very simple example. Yeah, and okay, I try to move it a bit, and let's go to our Lotka-Volterra problem. So first of all, we start to the numerical analysis of the classical Lotka-Volterra equations. So we looked for the fixed points, the so-called null claims, which mean the 0 claims, in other words, and what are the curves in the xy space which corresponds to those points where the derivative of x or the derivative of y exactly equals to 0, and we can visualize the vector field of this system, which means that you can determine the speed and the direction of the motion in the xy space in every xy point. And you can integrate numerically this system as well, which is a classical thing, that how the system behave in function of t, and there will be some point about the visualization. Okay, so let's see the details a little bit, not in a very detailed manner, but if you have Mathematica in your institute, I think it's very helpful to start to learn it, just because you can solve simple problems and you can check ideas very easily and very fast with the help of this software. So, example, we started with the clear the values of variables and parameters. It's sometimes it's very helpful because it can stack in the memory some values, and it can make problems in the computation. So after that, we give some numerical value for the parameters like this one, and after that we define the 2 functions of the right hand side. The one of them is the equation of the prey, and the other is the predator. So we define the functions in this manner. You know that some syntax is not so important here, but after that we numerically solve the fixed points here. So numerically solves the equation where the right hand side equals to 0 and the other right hand side equals to 0 in the conditions with both cases that it shouldn't be non-negative values, and we have to solve this for x and y, and we only consider the real values. And we store these results in a fixed points vector. And we define another vector which gives the null claims of the system. That is the so-called contour plot command. We look for all of the y values where this equation is 0, and all of the x values where this equation is 0. It is true just because the right-hand side of both the differential equations are equal to 0 if these two equations are valid, and we are interested in this interval of x and this interval of y, where these 0 claims are so these 0 claims are determined here. And after that, we, using by show command, we plot this null claims and fixed points together, as graphically we observe somehow that the fixed points, that the graphics command can put the points in the right place in the coordinate system, and you know that we label at the frames and we determine the size of the picture, and the label style is not so important. And I run this things, and after y, because you have to step in the kernel after y. Yeah, after y you can see the 2 0 claims or no claims and the 2 fixed points. The intersection of the 0 claims, that the fixed points of the system. Okay, that after that we can interested in how the system move in the phase space. The phase space is the space of x and y here. So in this space, how the system moves. For that, we numerically solve the differential equation. You can see the first differential equation and the second differential equations, and with the initial values, we have to solve these variables, and in the time interval between 0 and 100. And after that, we visualize this solution in a parametric plot, which means that we visualize the motion in function of x and y. This is the parametric plot, and we only give some additional modification to give a nice picture, that how thick is the lines and so on and so on. And after that, we go to what we have known already, that there is a closed circle in the phase space, the motion. Okay, so in the predator-prey phase space, this is a closed something. So this system is solved numerically, the differential equation, and after it is plotted with the parametric plot command did it. Okay. After that, I have said that the problem with the classical load converter system that the amplitude of the cycle depends on the initial condition. To show it, we use the parametric numerical solution of the differential equation, and you can see there is a specific command for that as well. So we solve this differential equation system, but the initial conditions are the parameters of it. That the init is the parameter, and we determine that, in the parametric solution, init is the parameter which can be changed. And after that, we gave a parametric plot command and make a table with the solutions depending on the init, and this init can change in a given interval. I have given the interval, and after that we have given the plot style just to make a nice plot. And what we have seen here, again, I run the simulation, that really we will get closed orbit for every initial condition, but this closed orbit are separated to each other. And we know that this is a consequence that this is a neutrally stable model. Okay, so we have already know a lot of things to this Lotka-Volterra system, and we can analyze the motion according to the vector field in the phase space as well. So let's define a vector with the name vector field, and we can use the so-called vector plot command, which consider the right-hand side of the differential equation, which gives the speed of motion in every xy point, and we determine the interval where we are interested in, and we add additional conditions how the vectors will look like in this vector space. And let us see how the vector space looks like here. You can see that, yeah, the motion is at that direction here. It's horizontal here, almost vertical here, again horizontal here, again vertical here, around the fixed point. Okay, so it can have a lot of information. If you have, for example, a much more complicated model, then the vector field analysis can help a lot. And now we can visualize all things together. So we use the show command and the first fixed points and zero cleans and the vector field and the phase space. We can plot it together with the simple command, and you can see here, okay, with the vector field and the actual motion in the phase space, and the intersection of the vector field is a stable fixed point or neutrally stable fixed point. Okay, and the last one, which is I think the most well-known one, just to plot the densities in function of time, which is simple. In the solve vector, we recorded the solution of the differential equation, and only we have to evaluate it again to plot it in the plot in function of t with some conditions to get a nice picture, and that you can see what is well known, that there is a periodic fluctuations of prey and predators in the model. Okay, as I mentioned in the morning session, that the problem, one of the problems with the classical Lotka-Volterra model, that it assumes that this is a neutrally stable model. I just want to move a little bit. So it's a neutrally stable model, and this is not structurally robust. For example, let's consider a little bit modified model. So this is the well-known Lotka-Volterra system, but we add that there is a self-competition between the preys, and parameter E can be a small parameter comparing to the other parameters. So there is some kind of very, very weak self-limitation of the growth. So without the predator, there is some logistic equation or something like this. And you can see that, let's assume that E is 0.01, which is 1 order of magnitude less than any other parameters in this model. And now the modification is that we added this part to the equations comparing to the previous one. And again, I look for the fixed points and zero cleans as before, so nothing has changed. But you have seen that one of the zero clean, actually the zero clean of the F, it's a little bit changed because in the previous model it was totally horizontal one, but it started to decrease just because of we introduced the self-inhibition. Okay, let's see after that the motion in the phase space, and it is a drastical change. you can see that now the fixed points became stable. So there is a cyclic motion towards the fixed point, but after a long time, the system reached the fixed point. Okay, so the periodic motion is only a transient one. And if you consider the vector field as before, you know, that you can use the vector field as before, you can see something very similar. So the analysis of vector fields can show us only that there is some kind of cyclical motion in the system, but we couldn't figure out whether it is a limit cycle, a neutral cycle, or a fixed point from the vector field, but we can some information that kind of cyclical motion can be observed together. And again, we plot all of the things which was shown before together, and you can see the zero cleans, the fixed points, and the vector field, and the motion in the phase space. Okay, and again, we can plot the variables in time, and you can see what can be seen in the phase space representation as well, that after a while that the periodicity decrease and the concentration tends to the fixed point. Okay, and now add another perturbation to the system just to show that how sensitive are these non-linear dynamical system, the details, and why you have to be very careful about the to get conclusion from the behavior of the system. And okay, so we have some self-competition as before. This is the last term here, that the E times X squared is the self-competition, but we assume as well that there is a kind of saturation in the model, that the Holding to saturation function, which was used by Daniel in the lecture as well. And we add, it's again, if F is much bigger than the others, means in this case that the saturation is very weak effect. So we add F is 80, which is much bigger than any other parameters in the model. And you can see that the functions, the original functions modified a bit. We added the saturating effect here and the saturating effect here. And again, we looked for the fixed points and zero claims, and I show it together. We solve numerically the differential equation and the phase space and the vector field. And after that, I show them together. So I merge together all of the comments here, and wait a bit. You can see that it's again, the zero clean is banded a bit comparing to the previous case because it was totally linear in the previous case. Again, you can see that there is some kind of cyclic motion according to the vector field. And what's interesting, here you can get a limit cycle. Okay, so motion is periodic and it converges to a limit cycle. So it's a stable attractor. It's not a neutrally stable something. And if you consider the motion in time of in function of time, you can see that after a transient, it reach a fixed periodic motion. Okay, so you will get what you were waiting for, according to the observation of d'Ancona, that if there is some kind of interaction between the predator and prey, then it's typically generate a limit cycle, a periodic motions. Okay, so a little bit generalized case when we consider the competition model. All of you know this competition model when there is some self-competition and cross-competition between the individual species, and we have 4 parameters. It's again, the algorithm is absolutely the same. The difference is that we have a little bit different right-hand side of the differential equations. Actually, you can see that R and rho are the 2 growth rates here, and the parameters are A11, A12, and A21, and A22. are the interaction parameters, and I give some values for them. Okay, and after that, again, we looked for the fixed points and nucleus, and we visualized, plotted them together after we solved the differential equation, and we looked for the motion in the phase space. We determined the vector field, and at the very end, we plot the dynamics in time, which is the most common one. And you can see again that these are the zero cleans, and you can find the fixed points. We have actually 4 fixed points here. As you know, the motion is a very simple one because it's converged to the fixed point very soon. And you can see together all of the things, that the vector field shows that the motion is towards the fixed point, and the motion is towards the fixed point from that initial condition. So we have only one stable fixed point, which is at that case, the coexistence of the two species. And you can see the coexistence of these two species here as well. They converge very fast to this value. Okay, so Mathematica has another, among many other very helpful and comfortable commands, is a very, very good option. Then you can visualize dynamical system with manipulating the parameters in the real time. So you can use the so-called manipulate. You can see here the manipulate function, and you can define two equations. For example, in that case, we have two parameters, and A and D, and A is the self-inhibiting competition parameter of the competitive Lotka-Volterra in case of the one species, and D is this parameter again in case of other species. So we have two free parameters in the model, and we can modify this parameter online easily and can check the behavior of the system. So it's again a very good tool to figure out how our system can work, and it's very easily can check if you have some idea to analyze something. And again, we looked for the fixed points depending of the parameter, the null cleans depending of the parameter, the vector field, and we show together the null cleans and vector field in this manipulate function. And if everything is okay, but I have to check, yeah, the dynamics is on, but maybe it can work. And okay, you can see the vector field and the fixed points and the zero cleans, and you can see that originally this parameter, this A is 1 and D is 2, and you can change it, and you can see that if D is changed, then the position of fixed point change. It's a very simple one. And for example, if you change it for it to be, I wanted to show a case when there is no coexistence here. Okay, so if there is no intersection, then only the species Y survive here. You can read it from the vector field easily, that this Y equals 1.5 and X is 0 point is the only stable fixed point in the system. But you can analyze any two-dimensional system easily with the help of manipulate. Naturally higher dimensional as well, but it's even more complicated. Okay, as a last part of this very short demonstration, I would like to show that how can you use the Mathematica if you, for example, consider a larger general LV system, and how can you give them random interaction terms and so on and so on. And for the simplicity, I set the random seed with the same number. You know that you can start the random numbers from the same value. you can check the result much more easily if it is setted. And yeah, again, I cleared all of the variables, which is very helpful in case of Mathematica. And the size of matrix let be 5, which means that we have 5 different species. And we define the matrix A, which filled up with random real numbers between -1 and 1, and n times n matrix. And after that, I modified this matrix a little bit. If this random real is, if another random number is smaller than 0.2, then I set up the matrix value to be 0. You know, that is a connectance factor. And on the other case, we leave the matrix element the same. So some interactions are deleted randomly, symmetrically. And we set up that the self-inhibition coefficient should be -1, as is generally assumed. And we defined an array of replication rate to be 1. And as a first step, let's see this matrix in a matrix form and in the matrix plot form. In the matrix form, you can see in a matrix, and the matrix plot, as you will see, you can visualize in the colored form. Okay, so you can see as a matrix, this interaction matrix, and after that you can see, but it's denoted by different colors. When there is white, there is no interaction. And in case of warmer color means that this is a positive number, and in case of blue, colder colors, which means that the negative interaction somewhat. So it's a random matrix between random matrix interaction here. After that, we are interested in how can we visualize this interaction in a graph. So there are comments which helps to visualize the interaction. That this is the I don't want to speak about in details, because I think it's not so important, but much more important than you can add values and colors to the interactions, and after that you can generate the interaction matrix easily. That you can see that the negative interaction has correlated with red in this case, and the positive one with green, and you can see the 5 species interaction matrix here. And you can plot it together, just plot it together. This is a visualization in the matrix form, and in a matrix plot form, when you can visualize the strengths in the colors, and after that the interaction matrix in a graph. And the very end of that, just to solve this system numerically. So first you define the vector of the variables x, y, t, and after you can define the vector of differential equations when Ri is the replication rate, the Ai is the matrix, interaction matrix times the variable, and you have to solve it with the initial condition that random numbers are added to the initial values, and this is the n-dimensional system, and n is 5 in this case. And after that, if this differential equation system is defined like this here, you only have to solve this differential equation with the command NDSolve. It's a little bit NDSolve value, a little bit more complicated than before, just because you consider the differential equation system a bigger one, and after that, the very last step, that you have to plot this solution, this numerical solution of the differential equation system, and you can find the solution in function of t time. That in this case, you know that x1 disappear in the system, and the x2, x3, x5, and x4 remains in stable coexistence. So you have a real option to analyze larger system, and you can see that in a very compressed manner you can define anything in this software. Yeah, so this is not an open system, as you know, and relatively expensive, but if your institute has a right to use it, so it's legal to use them, you have a legal version, and I highly recommend to start to use it, because if you have any dynamical problem or any visualization problem, you can solve it with the help of the Mathematica. On the other side, Mathematica is important that it has a brilliant help. If you click to the command, and after that, if you click to the command to the right-hand side, click and ask get help, you will get a very detailed description of the command and examples of it, and options, and similar commands which can be used, and so on and so on. So you can find the solution easily. And even if you couldn't find the solution easily, there is a wide community which really can help to each other. If you Stack Exchange or the Mathematica web page, you pose the questions that you will get the answer very soon. Okay, so that was the part of my practical unit, and as I seen, we have some minutes left, and I have a question now, that in a real case example, how one could set the values on the models? I'm not sure I understood the question, but maybe I understood. Just let's see that these are the, now let's consider the simplest one, the first one, which is, I think everybody is very familiar with the classical model. So we have parameters here, but I can change the parameter easily. I say that, okay, A should be 1.4, and I can run the simulation again, and I get a different result, a little bit different results. You know, the fixed points is in a different place. Was it the question? So you know that these parameters are set up beforehand, but I can write a cycle when the parameters can change, or I can do anything with the parameters. As you have seen that you can consider the differential equation solution in function of parameters in the parametric, and they solve.